That's okay. All right. Okay. So we're looking at this one first, okay? So let's look at it. So obviously there's a periodic table, yay, okay? But I want to point out a couple things that are on here. So do you guys see in the corners, there's two images on both of the corners? Do you see that you have like a little atom, a big atom and a little heart? And in the top corner, you have a little atom and a big heart. If you flip over this page, this tells you what those stand for. So the heart is talking about your electronegativity. It also is talking about your ionization energy. If you want to add that, it might help. Okay, those are those trends. Electronegativity is your love for, you should not say protons. I just caught that today. You should say electrons. Okay. So it's how much your atom loves its electrons. Okay, that's what we're kind of looking for. And that is us personifying an atom. Please, just on a side note, they're not living things, okay? I think you guys got that, though. All right, and then the atom-looking one is your radius size. That's what that's showing, okay? Okay, then you have the reminder of periods versus groups, okay? All right, so flip this back over to the periodic table. So then you also notice we have arrows. So we have an arrow that is going across, and it's pointing to the right. That is not telling you a trend. Both of these arrows, the one pointing down and to the right, these are answering the question why. As in, if I ask you, which I will on the assignment, why is this one bigger than that one? It has nothing, it's not the trend. The answer is not the trend. The answer is one of these. It's either this or this, no matter what. I could be talking about radius. Why is that one bigger than that one? Well, because it had more protons. Okay, less protons technically. Or why does this one have a higher ionization energy than that one? If it's up and down, you're going to say has more layers or higher shielding effect. So these are your two answers. Those are your only options for answering why. Okay, so let's talk about what those mean real quick, and then we'll go into the trends. So higher shielding effect, what does shielding mean to you? Blocking, right? So just like, I know it's not cold outside, it's like raining outside, but if it was cold outside, if I had one layer versus 15 layers, the 15 layers block it more than the one layer, right? The cold. Okay, so just like that, as you move down your periodic table, we add another energy level, and then another energy level, and then another energy level, another energy level, and blah, 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 blah. Those are layers. So higher shielding effect means more layers. So as we move down the periodic table, you add more layers. Now, last period people were asking, oh, does that relate to the Bohr model? Absolutely. Energy levels, the circles, right? So the inner circle, then the next level, then the next level, then the next level. And remember, those come from what row am I on in the periodic table, okay? So when you're looking at this, as we move down the periodic table, we add another layer. So row 2 versus row 5, this one has 5 layers. This one only has 2 layers. So that would be our comparison, okay? Okay, so if I'm ever asking about something and they're vertical from each other, that's your answer, okay? Don't even think about it. Just look for the arrow that is going up and down. This one, more layers. There you go. And it's it. That's the answer, okay? All right. This one, we can cross out the ZEF because I don't really teach it that way anymore. That stands for effective nuclear charge, which should be like, what? No, what that's telling you is the nucleus, right? So it has higher number of protons. So what is evidence of having higher number of protons as you move across a periodic table? What number is increasing that represents the protons? The atomic number, yep. So your atomic number is increasing as you move from left to right. So atomic number increases. So if I'm talking about like scandium, which is Sc, versus Zn, zinc, and I were to ask you, why is zinc smaller than scandium? If I said why, right? You go, so I don't even care if it's wrong. If I ask you, why is this one smaller than this one? What's your answer? Higher number of protons. That's it. Okay? So these two arrows right here are just meant to answer the question why, which is what you're going to see on your assignment, okay? Now, all of that just now went over your head in your slideshow, in your lovely slideshow. After each trend is the why slide, and it answers the exact same question. So you can always use this as well, okay, to find your answer choice. You got that? We're all good? Okay. All right, so now let's talk about the notes page. So go back to the notes page. Just leave this one out with you. Okay, so let's start with the basics. Okay, all atoms want to have blank electrons. What is that magic number? Who remembers? How many do they all want to have? So it's called the Octet Rule. So what does that tell you? 8. Yep. So write Octet Rule down here. That's going to be important when we get to bonding. So the magic number is 8. So for the most part, everybody wants 8. You saw yesterday when we were dealing with like helium, that only needed 2, but don't worry about any of those exceptions. The general rule is 8. So if all atoms want to have 8, you ready for this? What family already has 8? Which group number already has 8 valence electrons? The noble gases. Okay, if you forgot that, look here on the new periodic table that I gave you. So above 13 through 18, you see the little numbers up here? Those are your valence electrons. So, 7 went away. But 8 was 18 right here. Okay? They already have 8. That's why they're noble. Everybody wants to be like them. Okay, group 18. All right, cool. So I'm going to come back to that. So make sure you remember it in 5 minutes. I'm going to ask you again. Okay, atomic radius. So atomic radius on here says it is the distance from the center of the nucleus to the outer edge of the atom. Okay, so the center to the valence electron. So in other words, it is the size of the atom. Okay? All right, according to your periodic table that you have, where is the large atom picture? Is it the top right corner or the bottom left corner? So it is your bottom left corner. So we're going to put the word big right here. We're going to put a big circle. Just right there. We're going to put the word small up here, and we're going to make a little circle. Okay? So atomic radius increases going to the left and going down. Going to the left and going down. So usually that works for people, but a lot of time it doesn't. Oh, okay. So we're gonna turn around and do one more thing to kind of help you out with this. Okay. What else do you notice on this slide? What did I add to this one? Oh, I'm thinking about like the big obvious like big snowman. Yeah, there's an awkward snowman on a chemistry PowerPoint, right? So it is the snowman. So this is the snowman trend, okay? So what we're gonna do, if you have a highlighter, cool. If you don't, I have a whole bag, so you can grab one if you want. What I'm gonna do is we're gonna make the trend. I'm gonna draw it on the big periodic table because I think it's easier to put it there. You can draw it on either one, okay? All right, so snowman trend helps you kind of line these up. So a snowman has a head, a body, and then a butt, right? And they get bigger. So we have the head is the smallest, then the body is medium, and then the butt is huge, okay? So we have our snowman, just like that. So just like our snowman, the top stuff is smaller than the bottom stuff. Okay? Then we're going to turn our periodic table. So sorry, I cut off my butt right there. There it is. Okay. All right. So we're also going to draw it going sideways because that trend exists sideways. So we're going to put the head over on the right-hand side, the medium body, and the huge butt. Okay? So what this shows us is small, medium, large. So as we move to the left, we get bigger. As we move down the periodic table, we get bigger. The places that this will help you on is if I give you two things. So for example, everybody sees Y, right? So there's a Y right there. And we have SN right here. If I were to ask you, who is bigger? This is what you're going to do. You say, okay, SN is the head because he's on this side, and Y is the butt. So who's bigger, Y or SN? Y. Yeah. Okay, so you just kind of line it up that way. Same thing if I had copper, so Cu versus Au. Copper is the head, Au is the butt. So you see the visual of it, okay? That's the point of the snowman. So use it. Don't guess, okay? All right, back to our little paper. Okay, so if you want to have the snowman on this paper too, you're more than welcome to. 7th period wanted to, so I'll just draw it there just in case. All right, so there we go. So we have our snowman. Cool. Now, why, you guys ready for this? I know you can do it. Why is Fe smaller than K? Okay, so you guys are just telling me the trend, but why? Why is that trend even there? Why is this one smaller than this one? Higher number of protons. So she looked up here. She said, okay, those are flat, so it's higher number of protons. That's the only answer you can have. That's it. Okay? All right, if I were to ask, why is beryllium, Be, smaller than calcium, or why is calcium bigger than beryllium, what would you say? More layers, more shielding effect. Exactly. Okay? That's how you use those clues. All right, let's go to the next trend. Ionization energy. So ionization energy is pretty easy. It just sounds scary. So ionization energy is the energy required to remove one electron from a neutral atom. So we're removing it from that outermost shell. So another way to think of ionization energy is effort. Effort. So what I mean by effort, does it require more energy to bike up a hill like this or to go across the flat ground? To go across up the hill, right? It requires more energy to do that. It is more difficult going up a steep hill. And I'm sorry, if you're a biker and you like doing hills, that's great. I'm not. So I have trouble going flat anyway. But going up the strong hill or the big tall hill is going to take a lot more energy than going across the small hill, whatever, the little whatever. Okay? So if I require more energy, it is more difficult to take it away. Okay? Okay. So on your paper, what we're going to write. If you notice, by the way, what did our picture change to? An ice cream cone. Yeah, exactly. Okay. So we're going to add that in a second, but let's write the words first. Ionization energy is the energy required to remove, so to take one away, remove an electron. Okay. So, sorry, I keep forgetting to zoom in. Okay. I can see it on my paper. All right, so to remove an electron. So, how difficult is what you're answering? Okay, so if I have high ionization energy, if I require more energy, it's very difficult to take it away. Okay, so how difficult? Okay, so on our periodic table, which one has the big heart? What corner has the big heart? AT, yes, AT. So put the big heart in that corner right there. Put a little heart next to FR. Okay? So this time we are increasing as we move to the right, and we are increasing going up. So this is the ice cream cone trend. So we'll draw it on the big one as well. But this is what we're going to do. Okay? So this is our little corner. That means it's easy to take away an electron from francium. It's really difficult to take one away from helium and fluorine. Okay? So very difficult, very easy. Okay, So on our big periodic table, I'm just going to draw in those 2 ice cream cones again. And I'll give you 2 examples, and we'll keep going, and we're almost done. Promise. I'm going to change over to the big periodic table. If you want to get another color, you're more than welcome to, if it'll help, whatever you need. So I'm going to draw mine with orange. I'm going to draw my sideways one first. So here's my ice cream cone. Okay. Going sideways, and then we have an ice cream cone just upright. Okay. So what this tells me is bigger or higher ionization energy, more difficult, less difficult. Less difficult, more difficult. Okay? So it's kind of where they intersect and things like that. That's what we're looking at. Okay? So if I were to say, why is it more difficult to take an electron away from fluorine versus lithium? Why is it more difficult to take one from fluorine? What would you say? Or I should say, why does fluorine have a higher ionization energy than lithium?
Because it's harder to remove the electrons.
But why? That's what ionization energy is. So why does this one have a higher energy level? No? Okay, so are they across from each other, or are they up and down? Fluorine and lithium. They're across, right?
Sorry,
So what's the answer? Higher number of protons. Do you guys see that? You're doing the across arrow. So if I ever ask you why, figure out if you're talking about side by side or up and down. Got it? Okay, so then if I turn around and say, okay, why is it harder to take one away from fluorine than it is from astatine? Sorry. Versus astatine. Why is it more difficult to take one from fluorine than astatine?
More layers.
Has more layers, okay? And actually, fluorine has less layers. I asked the question kind of backwards, sorry. So less layers makes it more difficult, okay? But once again, these are your answers to why. If I ever ask why, it's in the assignment on 2 or 3 of the questions, okay? All right, you guys got this. We're almost done. Here we go. Finish this up. Electronegativity. So electronegativity is the same trend, okay? It is still going to be our ice cream cone. Oh, we forgot to put the ice cream cone on here. So it is still the same ice cream cone, okay? Because it increases going that way and it increases going up. So, but here's the exception. Electronegativity is the measurement or the measured of the ability of an atom to attract electrons for bonding. Okay, so remember that question I asked you 5 minutes ago. Who already has 8 electrons? Because things bond because they need 8 electrons. So who already has that? Noble gases, exactly. So what we're going to do is we're going to come back to this. For electronegativity, we are going to cross out our noble gases because they are excluded from this trend. Now, side note, I don't know if you care yet, but technically they're not, because technically at xenon, they start bonding. Some of the noble gases do, but don't worry about that right now. For now, our trend, we eliminate them. Okay, yes?
Seeing as the periodic table is actually supposed to be round, would it be on there but like less or more?
Ooh. Wait, what?
So, seeing as like the periodic table is round, right?
Okay.
How would you tell where
It would be a screw, like a screw. So it's actually an inclined circle. So it's like a swirly going up. So then you would have those energy levels still. Yeah. Great question, though. Awesome. All right, so this is still our heart trend. So put a heart right here. Let's circle fluorine. Because we eliminated our noble gases, fluorine is our most electronegative element. Okay, we can put the little heart down here in this corner. So once again, it looks just like ionization energy, okay? Oh, I forgot to put the definition, sorry. Electronegativity is an atom's ability to attract electrons. And it's not attracting its own electrons, it's attracting another atom's electrons. Isn't that crazy? So Like oxygen sitting here, hydrogen's over there. He's like, hey, those electrons, come here. And he's totally attracting all those electrons. Kind of crazy. So anyway, that's what electronegativity is, okay? All right. So with that, once again, our arrows are going to the right. They're going up. This is our ice cream cone trend again. You can still use that. Just don't include your noble gases because they already have 8. They don't really deal with electronegativity values as much. Okay? They deal with ionization because they don't want you to take their electrons, but electronegativity is not as important until we get down to like xenon and stuff. Okay. Whew. Moment of truth. You guys ready? You ready for this? Flip this page over, but have your periodic table ready to go. Like this one. Leave this next to you. Flip your page over. We're going to answer these questions. It's going to be quick. It's going to be quick. So I know that you don't know the names of all your elements yet, so feel free to just shout out letters. But you're referring to your periodic table right here. So real quick as a review, snowman, which trend is the snowman? Size or ionization energy stuff? Size. Okay, that's its atomic radius. Okay, triangle or the ice cream cone is going to be your ionization energy and electronegativity. Okay, cool. So, you ready? Which element is the biggest on your periodic table according to our trends? You're looking at the snowman. FR, good. FR, because we had our sideways one shoved us all the way over here, and then we went down. So we were looking at this lower corner, okay? All right. Number 2, which element has the smallest radius? So you're doing opposite.
Wait, show me how you drew your snowman.
I had big, medium, small, and then small, medium, big.
And there's 2 smallest.
Well, okay, so remember it's kind of like you go up and then all the way over. And so it's between the 2 corners. So we're looking at this corner now.
Oh, so it's
HE here. Yep. All right, so the smallest atomic radius, according to our trends, is going to be HE. All right. List the elements in group 13 in order of increasing atomic radius. We're not going to list them. Don't worry, we're just going to say the beginning and the end. So, but let's figure out these words real quick. Group 13. So is that the vertical things or the horizontal things? Vertical, good. So we need to look at our group 13. So find group 13 on your periodic table. So right here, okay? And then this is the other thing, and you guys are going to laugh because you're going to be like, you're not going to laugh really, but everyone really does know what increase and decrease means. But then the minute we throw this in and we put ing at the end, everybody's like, and they get it backwards. So increasing, does that mean small to big or big to small? Small to big, good. So we would start at the top of group 13. So we would start with boron, and we would go to, that's actually thallium, but yes, the one that looks like that. So boron to thallium. Sorry, that is a capital T. I went off my page. All right. Sorry? This is, no, this is an L. It's a cursive L. So this should be like that. I'm sorry. I had messy handwriting. All right. All right, ready? Which noble gas, what group is that?
It's the
18, good. So group 18. Okay, has the highest ionization energy. So we want the highest number for ionization energy. So is this the ice cream cone or snowman? Ice cream cone, good. So according to our periodic table, ice cream cone, the bigger part is at the top. So we want the top of group 18. Who is that? HE, perfect. Good job. All right, which family, so we're talking about family. So is that the vertical things or the horizontal things? Those are vertical. So which group number, has the smallest ionization energy? So yes, so I heard somebody say 1, one say H. You guys are in the absolute correct spot. Does anybody remember what that family is called? What is group 1 called? Not the earth ones, it's the other ones. It's the alkali metals, yep.
I was thinking fire.
I almost wrote fire. Okay, all right. Number 6, list the elements from period 3. All right, so period, is that vertical or is that horizontals?
Horizontal.
Those are the horizontals. Good. So we're going to find period 3. So we're going to go 1, 2, third period. We're going to go across like that. So now let's see what the question is asking. So we're at the sodium right now. Okay. List them in order of, there's the word increasing again. So again, that's small to big. But this is now talking about ionization energy. So we want to list them small to big ionization energy. So who do we start with and who do we end with?
You start with Na, you end with Ar.
Yes, absolutely correct. So we start with Na, we go to Ar because we're following that ice cream cone trend. And Na is over here, Ar is on this end. Okay? We see how we're doing that? All right, question. Why does Ar have a higher ionization energy? Don't think too hard. Your answer is on your paper, you guys. Higher number of protons. That's it. Okay? You guys got this. You got this. All right. We're almost done. We're only going to do 7 and 8 because 9 and 10 I feel like are repeats. So we'll just do 7. Who's the most electronegative element? We circle them. Nope. So again, this is the ice cream cone, but we had to eliminate one of the groups.
Oh, it's
So we got rid of our noble gases, so therefore it is F. So our most electronegative is on this end, and we got rid of our noble gases, so it had to be fluorine. Fluorine. Okay, so we're going to put F. All right, and then who's the least? Who's in the opposite corner? FR. All right, good. You have the skills you need. You may proceed to the assignment. It is due Monday night, so you can knock it out. You could not knock it out. Life choices. You make them. Go fight, win. All right. Let me know if you need help though, okay?